This is lecture 1 from chapter 13. As you can see, it's going to be about radioactivity. So we're going to be talking about the atomic nucleus and radioactivity. So basically how we get those radioactive atoms, radioactive elements at the bottom of the periodic table, and what kinds of things we can harness them for. So the first thing to talk about is kind of what is radioactivity and where do we see it? So just radioactivity itself is the process of the breakdown of elements with unstable nuclei, and we'll see why they end up with unstable nuclei here in a little bit. All of the elements above number 83 on the periodic table are radioactive and will give off a combination of different radioactive rays. We're going to talk about 3 different types of radiation or radioactive rays that will come off of these different elements. And the thing is that radioactivity has been happening for all of Earth history and is happening all the time. So as you can see up here on our little chart, we've got background radiation, natural radiation. So some of this is coming in from outside of the planet. So we've got cosmic rays coming in from sources like the sun and other stars and so forth. And then we've actually got a good chunk of this radiation coming from Earth's minerals itself. So we have some of these elements that are above that number 83 that are in our rocks around us, and so they're giving off radiation all the time. Then some of our exposure is coming from our own medicine and diagnostic tests like x-rays. And then a very small fraction of our radioactive exposure is coming from consumer products. So there are radioactive elements in things like smoke detectors and some of the radiation, different types of radiation are coming off of things like television sets and so forth. So there is a very small fraction of radiation that's coming off of the products in your home, but a majority of your radiation exposure is actually coming from natural sources. So again, most of it is this background radiation. So what is causing this radiation? What is causing radioactivity? So nuclear force, first, what do we know about like charges? So what do you know about positive charges and negative charges in things like atoms? All right, we know that they normally will repel each other. If you bring 2 positive charges together, they're going to repel. You bring 2 negative charges together, they're going to repel. So we haven't really thought about this or talked about it, but think about it. The nucleus is made out of all protons, all positive charges. So if these guys are going to be made out of positive charges, why don't the nuclei just fly apart, right? Because positive charges should repel each other. Well, this is where this nuclear force comes in. There is this what we call the strong nuclear force that we discovered. The strong nuclear force is what keeps positive charges together, keeps these protons attracted to each other. The thing is that the strong nuclear force only works best at a short distance. And so you can see down here in our picture, they have to be very, very close in order for the strong nuclear force to be attractive. So strong nuclear force will be attractive, proton to proton, if the protons are extremely close to each other. So that's what this little diagram is showing you. So the strong nuclear force will be very strong, very attractive to each other as long as they're very close. And the repulsive force, the electric force that we talked about before, where they're going to repel each other, is going to be significant, but as long as the protons are really close to each other, the strong nuclear force is going to overpower it. So then why do we end up with these unstable elements? Well, it's the big ones, think about it, number 83 and larger, that are the unstable radioactive elements. Well, it's because the protons get spread apart and the nuclear force weakens. So when you have a small element, like this guy up here, the protons are close together, right? So you've only got like 3 protons and 3 neutrons. And so the protons are going to stay very close together, and that strong nuclear force is going to be able to be very attractive, hold them very close together, and overcome the electric force. So they're not going to be easily split apart because of that repulsive, proton to proton splitting apart force. However, when you get a large element like this guy down here, now you can see the protons get farther spread apart. You've got more neutrons in there, and we'll talk about what the neutrons are doing because they do have an important job. But there's more space to spread out the protons as you get the nucleus bigger. And as those protons get farther apart, now we have more distance between the protons, and now that strong nuclear force weakens, and it's not going to be able to hold them together, and they're going to be more likely to get pushed apart by that electric force that we talked about before, where the 2 positives are going to be repelled from each other. Okay. So what are the neutrons doing? So the neutrons work as glue to hold the nucleus together. So that's why the big elements like uranium and so forth don't just pop apart. So those neutrons are holding the nucleus together. So they're going to keep those protons from just flying apart, even though the electric force is wanting to pull them apart, right? That positive repelling force. The more protons you get in a nucleus, the more neutrons you get for glue. That's why something like uranium has way more neutrons in it than protons. If you think about it, the atomic mass is much, much larger than what we would expect, because when you get into the smaller elements, the number of protons and the number of neutrons is fairly equal, right? But as you get up into something like uranium, you get almost double the number of neutrons compared to the number of protons. And this is why you need those neutrons to help hold those protons in place as glue. So you need more neutrons than protons in our larger elements. Now, here's the interesting thing about neutrons. When a neutron is by itself, it will eventually decay into a proton. So if you look here, here's our neutron, and it's neutral because if you think about it, the way I've always thought about it, it's neutral because it contains a positive and a negative charge, right? They're squished together inside of there. But when it's by itself, it will split. And so you'll end up with a positive and a negative charge. You'll end up with a proton, and then it'll release an electron. So what does that have to do with our radioactive elements? Well, if the neutrons are surrounded by protons, it keeps the neutrons from breaking down. It keeps them from decaying into new protons. However, larger nuclei will have fewer protons to control these neutrons. This is kind of a downside of being the larger element. So you need to have more neutrons to glue the protons together. However, if you look here in the picture, you have sections where the neutrons are there to glue the protons together, but there aren't enough protons around all these neutrons to kind of keep them in control. And so eventually, one of these neutrons is going to decay, and it's going to turn into a new proton. So it will turn into a new proton. It will eject what we call a beta particle, an electron. And then eventually what will happen is we'll get what we call an alpha particle, and we're going to talk about these here coming up. But it's going to eject a section of the nucleus, which contains protons and neutrons. And now we're going to not just have changed the element because we added another proton, we're going to change the element because we're going to remove protons from the nucleus. Okay, so this is what the whole idea of radioactivity is as far as the base of the nucleus. So we need the strong nuclear force to hold the nucleus together. It's being held together because those protons are being held really close to each other. As you get bigger nuclei, the protons are being held together by the neutrons. But as you get bigger, those neutrons, you need more of them, and you need the protons to keep the neutrons in control. And you eventually get to the point where there aren't enough protons to keep the neutrons under control, and eventually they start to decay and turn into protons themselves, and we start the process of radioactive decay, as you see here in the picture, and we start to make new elements. So I'm going to now look at what alpha rays are. These are what this little ejected particle is. So an alpha ray is 2 protons and 2 neutrons that get ejected from the nucleus when that nucleus starts to decay. So this happens because you get that new proton formed, and that starts to alter the nucleus. And so you get this alpha particle ejected from the nucleus. These guys are actually the easiest of the radioactive rays to shield from because they're large. They are basically a little nucleus. They do have high kinetic energy because they are actually a big particle. So they can damage materials and tissue because they do have, that a large mass from being ejected from the nucleus, and they have that mass to them with the protons and neutrons. However, these guys can pick up electrons while they travel in the air because they have 2 protons. If they pick up 2 electrons as they travel, it becomes helium. So if they don't run into anything between where they are ejected and they hit something, they become inert. They become non-damaging because they become helium. And so these guys, as long as you can shield against them and they travel long enough between the radioactive source and any items that they might hit, they're not going to be super damaging. Oh, sorry. So what can you use to shield yourself against alpha rays? I mean, alpha rays will be shielded against just by something like your clothing because those particles are so large. Okay. Beta particles, on the other hand, beta particles, these guys are the ejected electrons. So these are going to be the guys that are ejected when the neutron decays into that proton. So it will have that negative charge, and it's going to be smaller than the alpha particle. So a little harder to shield against. So these guys can penetrate paper and clothing, so we can shield against alpha particles with paper and clothing. But we cannot use paper and clothing to shield against beta particles. So they can actually penetrate paper and clothing and make it to your skin to do damage. But we can use something like aluminum to protect ourselves against beta particles because they can't make it through anything as dense as aluminum or denser. So we can use something like aluminum or any material denser than aluminum to protect ourselves from beta materials. Or I'm sorry, beta particles. All right, I'm going to stop here and I will pick up talking about our last type of radiation in our next lecture. It's a little bit different than alpha and beta because it's not an actual particle that actually emanates from the radioactive decay.